Good day to all of you. We are team number 3, and today we are presenting our final challenge, Autonomous Puzzlebot Navigation. This challenge was divided into two main parts. The first was localization. In simple terms, we need to answer where is the robot right now. For this, we used a camera-based EKF localization algorithm. For this part, the robot uses the camera as its main external sensor. The camera detects Aruko markers, and those markers provide measurements that help correct the robot's estimated pose. We also had to consider geometry because the system needs to transform information between different coordinate frames, the camera frame, robot's frame, and marker's frame. Calibration is also important because the camera needs to know its own internal parameters to estimate distances and angles more accurately. The second part was unknown exploration. The navigation had to avoid straight paths between consecutive points. It also had to react to obstacles by going around them instead of stopping completely. And finally, the execution is a closed circuit so the robot can keep repeating the trajectory while counting laps. Overall, this challenge combines localization and navigation. The robot needs to know where it is, decide where to go next, and react when something blocks its path. Before explaining our implementation, it is really important to understand what a Kalman filter does. The workflow is very simple. First, odometry gives us a prediction. That prediction has some uncertainty. Second, the Aruko marker gives us a correction from the camera. Third, the EKF combines both sources and produces a corrected pose with a covariance, which basically tells us how confident the robot is about its position. The result is published in one topic, which can then be used by the navigation stack and visualized in Arvis. The easiest way to understand that EKF is to think of it as the robot constantly checking itself. First, it makes a guess using the wheel encoder's odometry. Basically, it says, my wheels move this much, so I should be around here. But this guess is not perfect. Because the wheels can slip, a little small errors can build up over time. Then, when the robot sees an Aruko marker, it gets a reality check. If the measurement makes sense, the EKF uses it to adjust the robot's position. If it looks too strange, it can ignore it, giving us an extraordinary result.
So here we're going to explain how we use a Ruko measurement pipeline for our localization. So the first thing we did was the robot captured images from the environment, and then we used OpenCV to detect the Aruko markers, and from the marker size and camera calibration, we estimate where the marker is relative to the camera. Then we convert that into the robot frame as range and bearing, and then that measurement is published to and later used by the Kalman filter to correct the robot's estimated pose. So in this slide, we can see the complete navigation architecture. First of all, Gazebo provides the simulated sensor data, and that includes joint states, camera images, camera calibration, and the lidar scans. Then the Roku detector receives the camera data and publishes visual measurements as marker ID, range, and bearing. Then these measurements are sent to the extended Kalman filter localization node, which combines odometry, prediction, and Aruko corrections to estimate the robot pose and the covariance. And finally, the tangent bug node uses the extended Kalman filter pose and the lidar readings to move toward each waypoint and avoid the obstacles. So this means the robot does not rely on any known map, and it navigates using localization and real-time sensor information.
So in the next slide, we talk about the covariance and the robustness and uncertainty analysis, which demonstrate images. On the image on the left, we have that without an Aruko detection, the filter relies only on odometry, and thus the covariance starts growing over time. Then we have that on the image on the right. After detecting an Aruko marker, the extended Kalman filter starts correcting the pose, the estimated pose, and the uncertainty ellipse starts shortening a little bit more. We use the covariance to ensure that the robots start navigating only when localization is reliable. Then we talk about our workflow for the autonomous decision making, and our navigation is managed by a finite state machine. The first state is where the robot waits until the filter, the extended Kalman filter, provides a reliable localization estimated. Then it moves to the next stage, which is motion to goal. When the uncertainty is low enough, it starts moving towards the current waypoints. If an obstacle appears, the robot temporarily leaves the goal-seeking behavior and switches to a safe avoidance direction and follows the obstacle boundary. As soon as the path is clear again, the goal switches again to the available state, and it resumes the normal navigation until the full trajectory is complete.
Moving on to our algorithm selection, we had to answer the critical question, why tangent bug? Since our environment is completely unknown, relying on global planners like A-star was out of the question. Instead, tangent bug operates reactively using our 360-degree lidar. And unlike bug 2, which just blindly follows a straight M line, tangent bug reactively seeks the best tangent point to minimize the total cost. It does this by calculating a heuristic, the distance from the robot to the tangent, plus the distance from the tangent to the goal. Its core mechanics are divided into 4 behaviors. First, motion to goal. If the path is clear, it steers directly to the waypoint. Second, discontinuity detection. It uses the LiDAR to identify gaps as potential shortcuts. Third, heuristic selection. It chooses the specific tangent that brings the robot closest to the target. And finally, boundary follow. If an obstacle is too close, it seamlessly switches to wall following mode. Implementing this architecture brought up three major challenges. First, we faced the navigation stuck problem. As we mentioned earlier, Bug 0 and Bug 2 failed in complex scenarios, leaving the robot lost and stuck in infinite loops at certain waypoints. Our solution was upgrading to Tangent Bug to utilize those heuristic trajectories. Second was spatial blindness. The base algorithm has no native way to understand its physical surroundings. We solved this by integrating the 360-degree LiDAR, allowing the robot to detect discontinuities and properly guide the tangent calculations. Finally, we dealt with localization uncertainty. Since odometry naturally accumulates error over time, the robot will eventually lose its exact position. To fix this, we relied on intermittent Aruka marker corrections, which collapse the covariance matrix and maintain a global accuracy throughout the entire maze.